To start off, we have some catching up to do with last time because I couldn't fit everything into that episode, which was my fault. The pacing was a bit off. So we are gonna start right away with our good old friend, the array, which last time I initialized, for example, like this. And to recap, we take any data type we have, could be one of the built-in data types that already exist, one of the primitives, or it could be a custom data type that we create ourselves, be that struct or class, doesn't matter. And by simply adding these square brackets after the type, we tell the compiler that we want not a single version of that data type, just a single entry, we want a whole list of them. And so this variable a is now pointed to somewhere in memory on the heap, that's important, where we have a list of integer values. Somewhere on the heap is now a sequence of tightly packed together integer values. And specifically, when we reserve the space, we need the new keyword because it is technically now a reference type that internally stores integers. So we need to reserve space on the heap. When we reserve it, we tell it we need space for integer types, specifically for 10 of them. We use these square brackets again to tell the system how many spaces do we need for the sequence, 10. And each entry in the sequence needs to have enough space for an integer. And also to reiterate that from last time, integer itself is a value. It's a value type. It's just a single number. So when we created this, there will be just a single list of integers somewhere on the heap that we can reference with a. If this was a class that we created, a custom type that we have, so a reference type, then what we would have on the heap is not a list of individual instances of that class. It would be a list of further references, further addresses to the actual instances that might be spread out everywhere. And I don't like that music. Let's skip ahead. Sounds a bit too techno. Not in the mood right now. That's not... let's just let it run. Who cares? Where was I? So with the value type, we have a now pointing to the heap, but on the heap it's the values directly. If it's a reference type, then a would point to the heap, and the sequence on the heap would then itself have elements that point to other points on the heap. Right? So that's important. It's not, if you have a class, if you have a reference type, it's not that you store the actual data efficiently on the heap. It's just that you store value types very tightly and efficiently. That is not to say that making an array of reference types isn't useful. It is very useful still. It's just not as memory efficient as value types would be. But that's the thing with value types anyway. To access the individual values, we would use, again, these square brackets that we add after the variable, because we need to access a specific element. You can think of it like the dot operator we have for classes, or structs, for custom types, where we can use the dot operator to access a specific field in that custom type. Only for arrays, it's a special type where we use these square brackets to not target the name of a specific field, but the position in that sequence with just an index, an address within that sequence, basically, the number of the element we want to see, starting at 0. That's important. We have 10 elements. The first one is at position 0, so the last one is at position 9. There's no position 10, because that would mean we have 11 elements. Keep that in mind. Again, one-off error, very common when you start working with this. is just to accidentally go from 1 to 10 instead of 0 to 9, and then you have issues because you try to access memory that doesn't exist. But if we do it like this, just like with the dot operator, we can either assign values to it, or we could read that value and store it somewhere else, or use it in some kind of calculation. In the end, this is just a reference to a value somewhere on the heap. What I didn't show you is that there is a different way to create this array. Let's say I want to just have 3 elements, and I go for a 0 is 5, a 1 is 7, and a 2, the third element, is, let's go for 11. Instead of writing it out like this, I can simplify it to, let's do that with another array, b, which is gonna be defined the same way. It's an integer array, b. But this time we simplify things by not initializing the array and then filling the data individually. We tell the compiler that this is effectively what we want to do, and the compiler will fill in the details for us. And we do that this time not with the square brackets, but with the curly brackets. The curly brackets so far have been used for denoting code blocks, but they do have some other uses. And for arrays, that's one of the better ones, the more useful ones, though there is newer syntax that can replace it. We'll talk about that in a bit. Today, a couple of minutes. I can just go 5, 7, 11. I can list the values, still used to the key combinations, still can't get used to this online editor. This will create an array B that is identical to array A. The compiler will see these curly brackets and it will understand that this is because we initialized variable B with these values. That means we want an array that has 1, 2, 3 elements. So compiler knows this is what we want. Create a new array with 3 elements. And we have the values 5, 7, and 11. So that's what we want at position 1, 2, and 3. So index 0, 1, and 2. It's just a simplification. The compiler knows that this means this. So it will do all that writing for us, which is very convenient. This only works, however, in this specific constellation where we do the full initialization of the variable. With A, I could do this. I can make one instruction that declares A, and then have a second instruction that initializes the value. One instruction just declares our intention to have a variable A. In our mental model, we add it to the table without any value yet. And then later we add the first value, which is an address to somewhere on the heap. I can't do that with B. This is not allowed. In this constellation, the compiler isn't sure what this is supposed to represent. Sure, you might know that this is an integer array B, so this is the same as this. There's no difference. Why would the compiler complain? That's something we might get back into sometime down the line. If I don't forget it, I probably will forget it. Just comment if you need a reminder of that, or if you want to remind me to mention that. But there are constellations in which this isn't as trivial anymore. And the compiler also gets a bit more complicated if you add that stuff. Anyway, this constellation is not allowed. Compiler will pretend like it doesn't know what this is supposed to represent, even if it knows that B is an integer array. In this case, you have to be a bit more specific, and you still have to do this part yourself. You still have to declare the variable and initialize it with the new keyword to reserve space on the heap for 3 elements. The only thing we can skip is this part, because the compiler might not know what this is supposed to be exactly, but it knows it has, whatever this is, 3 elements. So the count, that it got covered, just not the what it is. So if we tell it that this is a new integer array, then it understands, oh, so these are the values for the integer array, and there are 3, so we want 3 spaces, and we fill them with those 3 elements. You can do that, of course, directly as well. So this would be the more formal way to write it out. But I don't think you should use that if you can get away with this, right? I mean, there's no harm in doing that. It's just wasted space, wasted time typing it out. If you do it in one line, you can do it like this. If it's not in one line, if it's not directly associated with a new declaration, add the new and then the data type afterwards. Or you can go the old-fashioned route and do that completely by hand. Well, let's have a look at array A again. We start off with the data type int, and we wrap that into a sequence of that data type. So we have whatever type we have in front, we just add these square brackets to tell the system we want a sequence of this mysterious data type before it. And it doesn't really care what it is. Could be any data type, anything at all. Can turn anything into an array, including other arrays. This is a legitimate way to write out arrays, of integers. You just go backwards here. We want a sequence of something, and the sequence of something contains elements which itself are sequences of something, which then are integers. And when we initialize that, we also have to use 2 brackets, because we initialize a sequence of sequences. Keep in mind, we have 1 integer as the base type that we actually want to store, 1 pair of square brackets to denote that we want sequences of integers, and a second square bracket to denote that it's a sequence of sequences. This is a data type, this is a data type. These 3 together are also data types, so I could extend this to how many I want, though that's rarely useful. Given that logic, you might assume we put the amount of items we want in here. Maybe we want this as well. Well, the truth is, arrays of arrays are a bit weird. We put the number of elements we want in there. Kind of weird, I know. It's sort of breaking the logic a bit, but that's just how C# handles it. Don't think too much about it. The first bracket gets the amount of items we get, and the important thing is that it's only the very first main sequence that we determine here. So this main sequence, this first sequence, has 10 elements, and each of those elements will be another array of integers, but those aren't defined yet. That's what we can do here. We can say A0, for example, is a new integer array with 2 elements. This is an array of arrays. So if I access one element of this array A, what I'm getting is another array. This references another array. So if I want to store something, I can't store number because this is another array. This is another sequence. This is supposed to be an address. So I have to provide another sequence, another array. And now I can go A0 to get the first sequence in my main sequence. And then I get another square bracket to add maybe the second element, to set that to 3. You imagine it like we have a sequence 1, 2, 3, 4, 5, 6, like that. That's one array. But now we have one sequence, 2 sequences, 3 sequences. And those ourselves are in a sequence. We have one sequence of of integers, one integer array, 2 arrays, 3 integer arrays. And those collectively are packed together into one bigger array that stores smaller arrays. That's what we do here. We started with 10, let's maybe make this into 3. If we start out as just new int 3, like this. What we have now is an integer array A, which contains 3 positions, which right now are all null. Memory is initialized as just zeros, and because arrays are a reference type, all zeros means null. Then we change A0, the first element, to a new integer array with 2 elements. So new array with 2 elements, which are going to be initialized at all zeros. So this is what we get after this line. And then we pick out the first array in our main sequence, this one. And on this one single array, we pick out the second element, position 1, this one, and set it to 3. We can also go A1 equals new int 0. Remember, a sequence with no elements is still a valid sequence. It's just empty. So the second position is set to an empty list, an empty array. A sequence with no elements. Valid and sometimes quite useful. And the third position, let's maybe clean this up. That could be a new int, which let's this time use the initializer we learned before. 1, 2, 3, 4. And that's what we get down here for the third position. So A itself is this array, which contains 3 elements. This one array, this second array, this third array. And these arrays are all independent from one another, and we can access them through indexers on the main array. And then, that's fine. So main array, and within these arrays, we can also use an indexer, then again, to access specific values in those. So A2, and then 3, that's this 4. 0, 1, 2, all right, so we're in here, and then 0, 1, 2, 3. That's this one. This is called a jagged array because it's an array of arrays where the smaller arrays, the interior arrays, are not all the same size. It's all over the place here. Some are longer, some are shorter, maybe some are even null. That's something you might have to be careful with. So if I put it like this. And these are useful in their own right in a lot of cases. But there's one special case which gets a special treatment in C#. What if I want all arrays to be exactly the same size? I want 3 arrays, sure, but I want all of these 3 arrays to be exactly 2 elements long. I should probably change this to 3 as well. Probably would do this in a loop for int I equals 0, I less than length. Remember, arrays are special reference type in a way, very special reference type, so we can access certain fields like length, which gives us the total amount of elements. So dot length will give us this 3, and that lets us go through all the elements within the array. Just use the I in here. That will iterate through each entry in that main sequence, which we then can set to a new integer array. So if I change this to a 4, so yeah, sorry. This is the result we get for A. Very common way to do this. And this might not be a 2, but maybe a value calculate from something. Like maybe you actually want this. So with this you would have totally square shaped. And with a 3 then you would get this. Special cases though. You might want to create this, for example, for math-related stuff. Essentially what you have here is a matrix, where a single array would be a vector. And there are good reasons why you might want to work with this. Even if you don't directly make math equations work as algorithms, it's used a lot for a lot of physics engines and graphics engines. Actually, a lot of really efficient algorithms boil down to some math. So it's not uncommon to use, but it also might be a simple table. You have columns and you have rows. 2 columns, 3 rows. You want to store data like this. To log something. Maybe you have a temperature sensor and you want to log all the different entries. You could write that data into columns maybe for each hour of the day, and then each row represents a different day. Just an example. And you can extend this. Naturally, you can extend this to 3 dimensions. Instead of a 2-dimensional matrix, you have a 3-dimensional one or a 4-dimensional one, even if they get rarer. These very balanced jagged arrays basically have the downside that even if you create them this way, you never have the total certainty that this is exactly balanced out. These are all equally sized, reliably, and initialized. It's also a bit less efficient than a normal array, because you have the first array, which holds references to other parts in the heap, to very different parts on the heap with further sequences of integers. So you have to read the reference for A, the address for the first main sequence in the heap, which then points to entirely different parts in the heap, which itself then contains sequences of integers. Sometimes, instead of doing it like this, you then default to doing it like this to make it more efficient. Instead of an array of arrays that gives you a full matrix, columns and rows, you just create one large sequence with all the necessary entries, and you simply keep in mind that these are technically split into rows. So even though it's one continuous sequence, you just remember how many columns there are, and then you can split that in your head into individual rows. So I can go const int rows, which will be 3, and const int columns, which will be 2. This will be rows times columns. That will get me 6 entries. And if I need to access a specific position, it's a simple math equation. I still have index 0 to 5 that I can access. But if I want to go through a specific row and column, well, I can start by giving me the row I want. So row, so int r2, let's go 1, and in C equals 0. So I want row number 1, column 0. So I want this value. Well, I multiply the elements per row times the row I want, and then I add my column to that. Sorry, wrong way around. I have to multiply the columns times the row. Yeah, I flipped this on the head, basically. I have 2 columns, so with every row I missed, well, I have to skip 2 elements. If I want row 1, that means I have to skip the first row, which is 2 elements. So 1 times 2 gives me a value of 2, and that means I'm now at position 2 in the array. That's this. And to that added, I want the column I need, which is 0 right now, so we stay at this. If column was 1, we go to this. If I need row 2, we skip the first 4 elements. 2 times 2 is 4, so we go down here. Very simple calculation. Just have to keep the rows and columns straight in your head. You have to remember which is what. But it works. And to help us out with that, to make our life a bit easier, C# has a special syntax for a special type of array, where we don't have to make those calculations ourselves. We tell the system we want a matrix, we want 2 dimensions. I simply add a comma in here. Instead of just we have a certain amount of items, a sequence directly, we want a sequence which itself is split into different dimensions. I now have 2 dimensions. Now I have 3 dimensions, 4 dimensions. Let's go with 2. This is still one sequence of integers. In memory, this will be just one long sequence of integers still. No different from this. It's not a jagged array. It's one straight up list of integers. In the computer itself, it will look like a normal integer array, but the compiler will do all the calculations for us and make sure the computer knows that we cheat a bit here. And just as we add the comma in front to declare the variable, we have to add it in here to mark it down as we create this special type of array with multiple dimensions. And when we add the actual values, where before we would say 6, we also have to split that up into 3 and 2. Our columns and our rows, or our rows and our columns. The computer doesn't care. If you decide this is rows and this is columns, then just make sure that you always say the first value represents columns or rows and the second columns or rows. You only have to keep that straight in your own program. Once you have that defined, stick with that exactly everywhere. It doesn't matter for the program which you prefer. Earlier I did 3 rows and 2 columns, so that's what I'm going to use. I have first rows and then columns in my case right now. That's how I define it. Computer doesn't care. This will effectively create a sequence of 6 integers or zeros so far on the heap. But if I access that, I don't go 2, 3, 4, 5. Instead I want row 1, column 0. And internally, it will do the same calculation I already did. Multiply by the first dimension, or by the columns, multiply 1 by 2, and add 0. And that's the position in that internal array, single dimension array that we have. We can assign a value, or we can read a value, like that, just like with a normal array. This will, keep that in mind, it's only one pair of square brackets. This will result in a single efficient array on the heap. We just have an easier time accessing individual values of a matrix, in this case, a 2-dimensional array, it's a matrix. And because it's initialized in this way, we know that we have exactly 6 entries, all initialized with 0. We don't have to worry about any nulls in there or worry that any columns or rows might have different number of elements than the others, and still gain the advantage of efficient compact memory. It's very useful. The only special thing here is you have to be careful when you look at something like length. You still can access length, and this would behave like a normal array. A.length is the total number of elements in there, because internally it is a normal array. And that's 6 elements. We split that up in our code here into 2 values, rows and columns, but internally the computer treats it as just a single array. So A.length is 6. But if we want to iterate through the rows and columns individually, we need to know these values on their own. We don't need the total number of elements. If we want to write a for loop that goes through all the rows or all the columns, we need to have those boundaries. And for that, we can access first another field called rank. Just like length will give you the number of total elements in your array, rank will give you the number of dimensions in your array. So for us, that is 1, 2. 2 dimensions. Rank will tell us 2. You might not need it a lot, because usually you are perfectly aware of what kind of array you have, but this might be important at some point. Keep that in mind. Rank is what you want. That gives you the number of dimensions. And if you know how many dimensions you have, you can use, instead of length, you can use the method called getLength. You can write. The name should be familiar to you, or the style of the name. We have a field called length, and we have this method called getLength. It's formatted like a getter method, which it is. And we use a getter method because we are not privy to the internal mechanics of this. The exact values are kind of hidden internally. We can use the field length, but that gives us the total length of the full array, not the individual length of each dimension. That's hidden, so we need a getter method. But this length could mean different things depending on which dimension we're interested in. So we have to provide a value. That could be 0 to get this first dimension, or a 1 to get this second dimension, or a 2 to get an imaginary third dimension, which doesn't exist, so this would actually break everything. This is where the rank might be important. If you want to iterate through all the dimensions of an array like this, you would have to stop at rank -1. If you have 2 dimensions, you have to stop at 1. But this would give me a 2, and this would give me a 3. Special type of array, so you need some special access to the length values. Length will give you 3 times 2, length 0 will give us 3, and length 1 will give us 2. We can use that in a for loop to go through all the rows or all the columns on their own, or do something for each column, for each row. Actually, let's just for sake of completion, let's do that. Int let's go row, and row equals, we start at row 0, and we go for row less than a dot get length 0 plus row. And then internally we do the same again. I'm gonna be lazy and rewrite this. Column is length 1 plus column. We can do int sum equals 0, and then we do sum plus equals a row column. For example, if we want to sum up all the values in this array, we can combine 2 for loops, each bound to a specific limit for their specific dimension. Rows, columns, that's how we defined it at least. This is supposed to be rows, this columns. The name doesn't matter. After all, this could be the rows and this could be the columns. It's just how we defined it. The first one is supposed to be the row for us right now in this program. The second is the column. We sum them all up, done. And that's where I'm gonna stop for the arrays, because we have another topic to discuss. This would have all been in the last episode if I did my pacing a bit better. Let's go back in time. And let me drink something first. We have quite some fancy tools nowadays. A few episodes ago we talked about how the compiler tells you if something is wrong, specifically where it's wrong and what is wrong. In the very beginning, computers weren't that fancy, and output wasn't that fancy. You probably only had a few incandescent light bulbs that would suddenly blink or light up or something, maybe a buzzer. If you're lucky, you had something like a 7-segment display or something that would show you numbers. That would be really advanced. And that's the best you could get at some point in time. So how would you make sure that whoever operates the computer will understand the difference between there is an error in the calculation, there was a division by 0, or the input was invalid, you made a mistake there, or maybe you had a weird situation where the compiler, not the compiler, where the computer had to suddenly run an operation that doesn't exist. All these different errors that could happen, or odd situations that you didn't account for when writing the program. The computer needed to tell you somehow what's exactly going on, as best as it can. So you had a limited amount of signals. Let's assume you could get a number out at least. In the end, you could still light up a huge row of light bulbs and figure out a binary value. That would still give you a number. What you then would have to do is read the manual, which would list that one is division by 0. And 2 might be unknown, not cone, unknown opcode, like an operation that it doesn't understand. Or 3, no input. Maybe you forgot to enter something, or you were out of punch cards. And this will be all put into a manual, so the operator knows what's going on. You see a number and you translate it, well, just looking at this table in your manual, and you know what's happening. You translate computer into human. Going a bit further in the future, computers generate a bit more fancy output. You yourself, as the programmer, might have a lot of stuff you want to tell the operator, not because of error codes, but just as part of your normal operations. You might want to tell them, hey, I need the next batch of punch cards, or I need to get the fiscal results for year 75, whatever. Just some feedback for whoever is sitting in front of the computer and needs to operate it. Again, more operator feedback, just less focused on the computer can't work and more focused on my program can't work or needs something or is giving you just some information for you to deal with. So just like with the manual before, you add out a manual that will simply go, 1200. That number means negative balance on some account. Like you figured out there's an account that has a negative balance. Someone's in the red. Maybe you're working out the budget constraints for the next year. And 1201 might be out of stock. Like you manage your inventory and you get a warning from the program that tells you, hey, there's a warehouse that's missing a certain item. And just like before with the old manual, you still have to give out this list of translations for numbers to meanings, whoever is operating the computer. Your program is basically useless without this list, because no one would ever understand what these codes mean otherwise. But now you start to run into an issue. With a computer, at least you are all forced to use the same machine, because they were expensive and there weren't many around, and sure, these were made by the manufacturer, and everyone in your team, in your building, in your university knew these codes by hand. Well, maybe they knew it off the top of their head, but they all had the same manual and could read that up. But this time, it's all values from your own program that you wrote. Software. Someone else might write some different piece of software which has also the need to output something, and they also go, yeah, let's go for 1200. That means, what could that mean? Student failing. You keep track of all the students in your university, and this thing warns you that, hey, there's someone who's about to fail. Maybe check what's going on there. Doesn't have enough credits. And this code is the same as this one in your program, but it has entirely different meaning. So now you have to give out manuals for your program, and they have to give out manuals for their program, and you have to be very, very sure that you have the right manual for the right program at all times. And if it's not very clear which program you're running and which manual you're holding in your hand, this might cause confusion. Maybe you make an update to your program at some point. Make an updated version, which has more detailed information. So instead of 1201 being out of stock, it's now 1204, and 1201 is now credit below cutoff. Maybe it's just an extension of negative balance. Like a negative balance is okay, just a warning, but in this case there's a lower limit below it unacceptable, and this is a separate warning for that. Not just negative balance, but negative balance below a certain cutoff limit. And you just assign that as the next number after negative balance because it makes sense. It's just, it belongs to this thing. They should be close in numbers, that makes sense. But you had to move then the out of stock to a different number. Now someone in your department tries to use your new program, but they still use the old manual. Because they don't know about the update, for example. They still have the same program, they are sure that they got the right thing, and they got suddenly some weird messages that don't make any sense. Or even worse, they get messages that make sense in their situation and they get the wrong conclusions. Maybe someone else left a program running from a previous test for something else, maybe from a different program, and the operator didn't notice, and they get all these error messages for a completely different program. Maybe someone else misplaced the manual, or some made just a sticky note somewhere with some new codes, and you don't know which program it belongs to, and you assume it belongs to your current program, and suddenly doesn't make any sense anymore. So you have to agree with everyone else on the campus that you all pool together your numbers. It happened one too many times that you just ran out of stock and suddenly thought every student in your year is failing classes. Cause a lot of issues, a lot of frustrations. So you all sit together, every department, every programmer, and you all agree that we create one large list of codes. Everyone gets a reserve of, let's say, 100 different codes. You get 100 to, or 1,200 to 1,300, and the next one gets 1,300 to 1,400. And if ever you need more than that, you can schedule another meeting and you reserve another block of numbers. You make sure that whenever you create new messages, you don't try to place the old ones. You just add to your existing stock of outputs, so that the old values will always be the same. If someone has an older version of the manual, the code still makes sense and will still give these same messages. And this works for a while. But it becomes very inconvenient. You notice that since I can't update the old meanings, even if I change barely anything, I have to waste precious numbers for a slightly different output. Let's say for the out of stock, I add a specific, like where. Okay, I'm dropping the connection. Right, let's... There we go. Out of stock in warehouse south. And maybe I have a second message for store entry A. Or maybe lounge. Maybe I have a different out of stock warning for all kinds of stores or places where I keep stock of something. And for each of them, I would have to create a new number and this new warning message or error message. And that just wastes so many new numbers that at some point you have to apply for a new block of numbers that is entirely your own. And it becomes harder and harder to manage exactly which messages you already have and which ones you could reuse, because it's the same message still. Because you have hundreds of possible outputs and you have to track, did I use that message before for something? So instead, you get clever. Instead of making one specific output for everything, you decide you make a combination of outputs. You don't output a single number, you output two numbers, or three, or four. You output a sequence of numbers. You have the out of stock for 1004, and then you make a little asterisk in your manual, read the next number, and then you get 1250, for example, for warehouse south. And maybe 1051 for lounge. And you can combine these two to tell the user that a specific part of the campus is lacking a specific item. And you don't have to write thousands of new messages, because now you can combine these with other messages, like you're running low on something. You're not out of it, you're just running low. But you only need this one extra message, you're running low on stock, and still can reuse the location codes. And if you have these location codes, maybe you can coordinate with other departments that also find they need these location codes, or at least some of them, so they can reuse yours. You just give them your codes and you say, hey, I assigned this code to this name, to this location, and they can reuse it. Combine that themselves with their own messages. And you slowly piece together this entire language, so to speak. All of these special words, locations, short messages that you just pick and choose to create full-on messages, sentences, just with a string of numbers. But even this has limits. It becomes even more silly now. Sure, you don't waste as many numbers anymore, but working with these gets a lot more complicated now, because I have to figure out a way to write this sentence. Which messages do I have already in the pool of existing codes that can be pieced together to form that message I want? And that can take a while. So, at some point you have another meeting. It's a couple of years later. Computers have a lot more capabilities and more memory. Why don't we make use of all this technology and break this down to the simplest alphabet we can think of? Our alphabet. Just the straight up alphabet we have. Instead of error codes or specific numbers referring to error codes or specific messages or words, we have codes refer to specific characters. We have an alphabet. In their case, maybe you had 26 letters. Not everyone has, but they might have. And so we dedicate maybe 2000 to A, and 2001 to B, and so on. And if you ever need to output something to a user, you give them a sequence of these numbers and you piece together a regular sentence. You don't have to worry about any predefined messages in a manual. You just give them a table of what these mean, a bit like Morse code, just numbers instead of dots and dashes, and you give them a full-on message that way. The ultimate freedom. You don't need to look up a lot of things, you just need to know what do I need to output, which letters would that be, and which numbers do I have to output in sequence. And maybe, because technology has advanced a lot, you have some fancy peripherals on your computer that understand what these numbers mean. You just wire it up yourself that way, and they can print that out on a piece of paper. Like an electric typewriter that simply is overridden by these codes and gets a different signal for every one of these numbers, and you write all of that out on a piece of paper, so you don't even have to look up a manual anymore. The programmers will probably still have a table, so you know what to input in the program to output something on the electric typewriter, but then the operator doesn't need to look this up anymore. You just get the full-on text. And because you have all the letters of the alphabet, you don't really need to worry about any more numbers to reserve, because you can already form all the sentences. Until at some point you realize, hey, if we have this system that can output numbers, that can output letters-based numbers, can we do a bit more fancy stuff as well? Like, my typewriter has a new line. I have the new line key that I can press to advance to a new line and write something more there. Or the tabulator, which moves everything a bit further to the right, so I can format my text a bit nicer. Maybe I want to go back one key, move my carriage a bit back, and hit the letter again to make it a bit more bold, to make it stand out a bit more. So you add a bunch of extra codes that don't correspond to letters directly, to characters. Instead, they refer to control codes for the electric typewriter. Just the program outputs a number. That doesn't mean show the user this letter or this letter. It just means, hey, tell the typewriter to move the carriage to a certain position and do something else. And it works, and it makes for nice formatting. Now your program doesn't just give out a normal line of code like a Morse code. No, you're more advanced. You can write out full formatted text. And then you realize, if I can output all of that, why should we limit ourselves to just these letters? And they're nice symbols, they work, we can write stuff, but Sometimes I want to write some lines to highlight something. Maybe make some dots or dashes here and there. Why shouldn't I be able to draw something? I just need to make some lines, some diagonals maybe, some vertical lines, some horizontal lines. Maybe a few boxes here and there, some special symbols will be added. Maybe the math department wants to automate some stuff and they need a lot of Greek letters and some odd symbols to write out all the equations and make that work. And alright, so we do reserve some blocks of codes yet again for some special kinds of operations and characters and symbols and graphics and whatnot. And they all get put into this one table we have with all kinds of weird stuff going on. Like, make a sum symbol and maybe 4000 is just a box with some diagonal lines through it. Who knows? Who cares? We have the space and we can make the system react to that. It gives us a lot of flexibility for our programs. We can make really nice output now for the users. And not just output for the users, if we can write that out on a typewriter, nicely formatted, we can have something we can put in these newly fangled copier machines. And have really nicely written text that are completely automated, calculated by a computer very quickly. Don't have to worry that much about my formatting anymore. Just give it some simple numbers and the program will turn that into a nicely formatted question sheet for my next exam. So far, huge success. And you turn this table into your personal success story for your university. And you want to share that with others. Turns out you're not the only one that can think that way. Other universities, and industries in general, have done pretty much the same as you did, because they had the same issues. And they all had their own little list of numbers that correspond to symbols. And because they all had their own priorities and order in which things happened, the numbers are very different from yours. And the available list of symbols and characters and controls vary wildly depending on which industry and which place of the world they came from. After all, not everyone has an alphabet with 26 letters. Some have less, and some have way more characters than that. So, you now have a problem. You want to share your program, your progress with other people in the world. But they all have different ways to interpret the numbers your program would output. They all have the same idea, but you write ABC and they see a sum symbol and a control character for carriage return. Doesn't really help. What you need is standardization. Not just in your own campus, you need to do that between all the people that want to participate in this shared large project of we want to share our stuff, our programs, our advances. And of course there have been many such organizations and groups over the years, but the big important one that we need to talk about now is the Unicode consortium. Unicode is a term that you've probably heard before. You can think of it this way. There's this large organization, this large international organization that has successfully maintained this list of numbers to characters, basically. That's their main purpose, or one of their main purposes. They have the master list, this one table of what character is represented by which number. It's still all just numbers that represent special symbols and characters and certain behaviors. And they determine what goes to which number. And if anyone needs new symbols or characters or something, they can go to the organization and apply for it. And the organization will then assign them a specific series of numbers to represent whatever they need, if they don't already have ways to make that happen. Unfortunately, reality isn't quite that easy. Just having this table of numbers is not enough. The current list of numbers this organization stores is with it somewhere a bit more than 1 million different codes. The list of numbers they maintain is right now about 1 million, a bit more than 1 million. And this large table is, well, you need to write down one number of this table for every character you write. So even something as simple as hello will have 5 characters. We have 5 different letters here, and each of them has to be represented by a number that could be 1 in 1 million, in more than 1 million. What kind of number do we need to store at least 1 million? The real-life answer would be about 21 bits. That would be enough to store every single number we currently have referenced in this master table. But we are programmers. We think in multiples or powers of 2, more specifically powers, not multiples. And the next power of 2 would be 32. Convenient because we already have 32-bit numbers. We call them integers, or int in C#. 32-bit integers. Well, 32-bit integers. We don't really have to worry about negative numbers, so technically these would be unsigned integer values, but doesn't really matter. So each of these is represented by a 32-bit number. This text alone has 5 32-bit numbers. Just this very short word, hello. Think about how much space you would need to store a full letter, or a book, or a library full of books. Even your chat messages right now take up technically a lot of space. And we are in the early days now, going back a bit. Memory is premium. I mean, it is, again, right now, circles and all that. How can we optimize this a bit? We can figure out a way to compress the data. Compression is a topic we need to come to at some point again, but it boils down to figure out which characters, which symbols, which control characters and whatnot are the most common ones, which are used most often. So when you write a text, which characters will be put in there and the most? And once you have this list of probabilities of likelihood of being used, you can arrange these different characters in your list in such a way that the more common characters, like alphabet, will have smaller numbers. And that can be used then to advantage by coming up with a scheme where, let's say, I have only 2-digit space. We're not gonna worry about the binary values right now. We're gonna use just decimals, so from 00 to 99. Okay? So just decimals, 2 digits. We can write out 100 different numbers this way. 00, 01, 02, 50, 51, 52, 98, 99. If the 100 spaces we have with this are not enough anymore, we could simply add another digit, which is what we do in decimal all the time, right? Next would be 100. But we think of multiples all the time, of powers and multiples, so instead of just one extra digit, we add 2 extra digits. So at some point, we can go start from 0, 0 again, and then we add another 2 digits and make that also 0, 0. If we have a small number, we only need 2 digits. If we have a big number, we use the 4 digits. So if I write down this word with our characters, where the more common ones are smaller, that means I probably only need 1 or 2 digits for each character, and only if I have some special characters that are very rare do I need to add more digits. Write out the bigger numbers. Very simple idea. The only issue is that the computer wouldn't know that this is one 4-digit number instead of 2 2-digit numbers. So it's not quite as simple, as efficient. We could make something like 99 isn't a value that we can store directly. We can go from 0 to 98. And then 99 means read the second number afterwards. So the computer reads the first 2 digits. And if it's from 0 to 98, it means one thing. And if it's 99, it means read the next 2 integers, the next 2 values, digits, and they have their own meaning. So this way we always know how many we read. We don't have to worry about not knowing if it's 2 individual values or one large value, because this is only 99 if we need to read the second pair of digits. And we still get the compression of smaller numbers take up less space. And most common characters use these small numbers, so most text will be actually fairly efficiently stored. The specifics of how we make this compression work is separated into different standards, because there are different ways we can make that work. And the name was, I'm thinking of the full, so these are UTF something. That was Unicode transformation format something? But I'm pretty sure that was transform. That must be Unicode, this was transform. I'm not sure if this was format, DF. But there are several UTF standards that are also set by this organization that maintains those master list of values corresponding to characters or symbols. The most direct one would be UTF-32. You will see that very rarely. It is a straight up 32-bit number that directly corresponds to an entry on the table. No efficiency gains here, no compression whatsoever, it's just straight up. Every character will have a 32-bit number. That's it. The most straightforward way to write it. But because it wastes a lot of space, especially because we only need 2/3 of this in reality, keep in mind 22 bits would be enough. This is 11 extra bits for every character. Not very common in practice, but it is good to have because it makes everything very simple, and sometimes you want simple. The most common variation would be on the other end of the spectrum, which would be UTF-8. UTF-32 works by using 32-bit numbers. and each 32-bit number represents one character. UTF-8 works by using 8-bit numbers, where for the most common ones you only need 8-bit, but then when you have some more uncommon variations, you might need 2 8-bit numbers, or 3, or maybe even 4. So this is always 32-bit, or 4-byte. This can be 1, 2, 3, or 4-byte, depending on what character specifically you try to encode. And it's not as straightforward as a certain number in the first one means read the second, and then maybe a third. The scheme to encode data with this is a bit more complex, but it's not complicated, and maybe we'll talk in detail about how that works at some point. It's not relevant for you right now. It's just, you have different bytes that can be combined, and when you read a byte, you know by that value if you have to read a second or third or fourth byte after that. That is always known to you. You always know how many bytes you will read by reading the first byte and then cutting through. Same as with my example. The actual schema is a bit different though. Because it encodes the data, this is also called encoding format. UTF-32 isn't much of an encoding format because it's just using the numbers. Technically it is an encoding, but it's straightforward. UTF-8 is actual format where you have to keep up with the rules and keep that in mind. And you can break things by making invalid byte sequences that don't correspond to a value because they break the format. Just as you can break the 32-bit encoding format by applying values that don't correspond to anything on the table. 32-bit, way bigger than what we would need to store everything on the table, so of course there are values that are not on the table yet. Though they might come in the future. In between these two is... sorry, there's only one. You might think we have 32 and 8. We have UTF-16. And you might think we also have UTF-24. Well, we work in powers, so 24 doesn't exist, even though it would be quite a nice fit, since 21, 24, it's closer to the ideal. But no, we have... well, technically we have some more standards, but we're gonna ignore those. These are the 3 you should be aware of. 32, because sometimes it may be convenient to simplify things, and just to be aware that it exists. But the ones you will always work with are usually, most of the time, 99% of the time, either UTF-8 or UTF-16. UTF-8 is based on 8-bit, and UTF-16 is based on 32-bit, 16, 2-byte. I'm getting confused already. Yeah, 16-bit, so 2-byte. And you have either 2 or 4-byte. 2-byte is not enough to store every value. 16 is less than 21. So sometimes you need a second 16-bit part, let's call it that for now, which complements the first one and gets you to 4-byte to store everything you might need. So 32 uses the full 4-byte you might need to store everything. UTF-16 has either 2 or 4-byte, so it can be a bit more space efficient to store the most common values. And UTF-8 is possible to have 1, 2, 3 or 4-byte, so you have more granularity in between. For the smallest, most common values, a single byte might already be enough. And then you might need more bytes the more uncommon the characters get, or the later they get added to the table. Let's put it that way. Just heads up, you can save space with UTF-8, but it's technically not the most space efficient way. because the way the encoding format works means you waste some bits. So you don't actually use the full 4-byte, for example. Whereas 32 will use all 4 bytes for one value and leaves enough space for something else in there. UTF-8 uses all the bits to store the information, how many bytes you need, and the actual character you want to encode. So it's saying UTF-8 is the most space efficient is actually wrong, because it wastes a lot of space for the encoding itself. But in practice, you will need a lot less space to store in UTF-8, which is kind of paradoxical. It's not the most space efficient in a way, but it's also, it is. Depends on what text you want to encode. If you want to have a lot of unusual characters, it's probably better to switch to UTF-16, or maybe even to go to 32, or to make your own encoding format. I mean, in the end, it all depends on where you want to store it and use it. If you want to share your numbers, if you want to share a text with someone else, the best way to do it is using one of these standards. Because then you can both be sure that you know what your program is giving out in information, and someone else is also sure about what your program is giving out. You both are clear on what exactly your program is saying. Some terminology. These things, these individual bytes here and these 16-bit things, they're called code units. So the Unicode organization has this large table which has a bit over 1 million code points. I think 1.1 million was something. Code points. Each code point is one entry on the table. So one character, one control character, one special symbol or drawing, whatever. This is all that UTF-32 is. Each number represents one code point. UTF-8 and UTF-16 don't represent this code point directly. I mean, yeah, you write down code points with UTF-8 and UTF-16, but they encode these code points by using code units. They combine them to a code point. So UTF-8, you have 1, 2, 3, or 4 code units. To make up one code point. You can combine multiple code units, and combined they have enough information to denote one specific code point. With UTF-8, you have 2 or 4 byte, which is 1 or 2 code units. So the number in here, in the UTF format, tells you how many bits are there in each code unit. 32. We have 32 bits for each code unit, and each code unit is already a full code point. UTF-8, the most common one, will have 8 bit per code unit, and combining 1, 2, 3, or 4 code units will give you one code point. And UTF-16 has 16 bit per code unit, and you can combine 1 or 2 code units to get one code point. Unicode itself, the specific encoding formats and whatnot, is actually quite interesting to learn about. Though you don't technically need to understand it to work with text. Most of it is handled by the computer nowadays. There are libraries in the background that handle everything for you, and you don't have to think about it too much, which is good. But you can read it up. It's really interesting. There are some cool details in there that I completely left out. Like the way the table is arranged is not just for making the more common ones smaller to help make these encoding smaller. They are also arranged in a way that makes working with them more efficiently. And there's a lot of backwards compatibility, which is another reason you might choose UTF-8, because it has backwards compatibility to another older standard called ASCII, which wasn't that standardized worldwide. And there are other encoding formats that are kept compatible with this system by Unicode. So the table is arranged in a very clever way, and there's a reason why it works the way it does. People way smarter than you or I, or at least way smarter than I, have worked on that for decades. So Unicode, really smart system, really useful system, used everywhere by now internationally. It's one of the big standards that everyone just agrees on, because you need a standard for this. That's the most fundamental stuff, text. Everything else that builds on top of that, you can make your own stuff, okay, sure, standardization is still good, but do whatever. But at least the text itself, conveying information on the most basic form that the world has essentially agreed on, is this one standard. Now let's maybe focus mostly on this UTF-16, because UTF-16 is the encoding format that's used inherently by C#. C# internally, when you work with text in your program, it will default to UTF-16. That's what it's going to use. And so let's have a look at how text works in C#. Finally. Let's start with the most basic building block. We want to store a single character. Just a single letter. We know with a 32-bit number, we could store a value, and that will represent a specific number somewhere on the table, which corresponds to a specific symbol or control character or whatever. But in C#, there's a special type for this. We don't have to store it as an integer. We can store it in a special type that is also just an integer number, but one that the compiler understands as this is specifically for text. This corresponds to an entry on the Unicode table. And this special type is called char, for character. And I don't assign a value directly. I could do something like this, and for example go like that. I need to specifically cast it, but I can do that. In this way I would assign this character the number 65, which lets the compiler know I want to store in this variable a reference to entry code point 65 in the Unicode table. But as a programmer, you can't be bothered to look up that table for every single character you want to output to a user. So, since the table is standardized anyway, let the computer figure that out. I just want to store the letter A. Let the compiler figure out which code point that is and store that number in this variable. I just give it the letter A. Only now we have a bit of an issue. This A looks like a variable or maybe a field. Or since it's uppercase, maybe a type somewhere, a class, a struct. So the compiler thinks I'm referencing some existing data somewhere. It doesn't understand that this is just a number. This is basically a constant. This is a value. So I have to mark it specifically. It's like, for example, for float. If I write a float out, compiler doesn't like this because it thinks, oh, this is a floating point number. I store that as data type double. But I'm storing this in the float, so I have to add the little postfix here, f, to make sure that the compiler understands this 1.0 is a float. In a similar way, I have to mark this letter A to make sure the compiler doesn't think it's a variable or a reference to something else, but a value in of itself. And we do that by surrounding that with... And I think I switched my... This way? Yeah. Character layout was changed, or keyboard layout was changed. We use these single ticks in front and after the character. You can see I get some special highlighting from the editor here, it marks it in red, because this is a value. Honestly, I'm not sure why I need one in front and one behind. Just one behind or just one in front would have been enough, in my opinion, since it's a single character. Computer knows exactly how much it should be able to read, but again, people smarter than I, different people for the most part, have worked on this and they will have their reasons. Maybe it made things way more efficient or clearer or something. I trust that they had their reasons for why this is the better solution. In any case, this is how I tell the compiler this A is not meant as a reference to something in my code, it is a value in of itself. And then the computer understands, oh, you're referring to Unicode. So I'm looking up A on the table. I know A refers to the value 65. That's the code point. And that's what I'm going to store in this variable, which is specifically designed for Unicode values. It is still just a number. I could store letter in an integer, and this integer would now hold the value 65. Which, by the way, is the code point for uppercase A. That's just where it works. But because we write it in a character, the compiler knows we have to treat it a bit differently. It gets a bit of special treatment by the compiler, by the computer in general, because it refers to a letter. For example, I couldn't just... I think I can't. Might have to cast that as well. Okay, not important right now. Compiler would tell us if it's not working. The weird thing about character is only 16-bit. Character is in fact a single code unit, not a code point. As I said earlier, C# defaults to UTF-16. That's where it comes from. Character, the type in C# to work with text, is using UTF-16. A character, the char, is a single UTF-16 code unit, which for some characters, like A, is perfectly fine. That's all we need. A only requires a single code unit to be represented, so letter now stores a fully valid code point. It is already all we need. But for other characters, other symbols, a single code unit isn't enough. And one single sample would be this. An emoji, which are actually part of, let's say, master table of code points. Emojis are Unicode standardized. They have their own specific number on that table. The issue is this number. I think for this card would be something in the 100,000. Last time I looked it up, I think 120,000 something. It's larger than a 16-bit number, which would go at most up to 65,000. We need more bits to reference this code point than we have in a single character. In UTF-16, this emoji, this car, needs 2 code units, not just 1. So this doesn't work. See these ticks here, these single ticks, they also refer to a single code unit. They are specifically meant for char, for this character type. So they can only contain a single code unit within. If I compile this, we should see an error message. Too many characters in character literal. If you ever see this message, you have somewhere a character, the single upticks, which contains more than 1 code unit. It's the same if you have several characters in here. You can see the highlighting is gone. If I try to compile this, same result. Here at least it's obvious what's happening. You have several characters, not just 1. With this one it's less obvious, but it is the same issue. One emoji takes up more than 1 code unit, and this can only hold 1 code unit. Same as I can't store several values, several different integers in one single integer variable. I can't hold several code units into a character which only stores 1 code unit. How do we solve that? What if I want to store several integer values? We just did that in the beginning of the stream. We use an array, which holds a sequence of integer values, for example, or a sequence of Unicode code units, UTF-16 code units. And we can simplify that the same way we did in the beginning with the different initialization for arrays. We can go A, B, C. This array holds now a sequence of code units. And the sequence of code units could be a full-on text. So we can store a text that we might want to show the user by just storing it in an array, like so. And because our programs will probably work with a lot of text, especially for outputting to the user, there's of course a more convenient way to write this. Way more convenient. Just as we have a special type to deal with code units, we have a special type that deals with sequences of code units. And it's a bit of an odd one, because it looks like all the other built-in types, but it's different. It's called string. It's written lowercase, it's a primitive data type, kind of. It looks like the others, like integer, like char, like bool, float, whatever. But unlike this, or int, or bool, string is not a value type. String is a reference type. If you have a character and store that in a variable, that's just the value. It's stored on the stack unless you put it specifically wrapped inside an array or a custom type somewhere on the heap. But this variable now holds the value for this. Or let's put it in A again. Avoid the emoji for now. Text, however, is a reference to somewhere on the heap where we store text. Where we store an array of characters. String is hidden from your view an array of characters. Somewhere on the heap you have a sequence of individual code units of characters which combined give you one text, one sequence of code units, of code points more specifically. Well, actually no, string would be code units, it can be invalid. Let's hope you don't get into that situation. And when we want to create that, just like we did up here, we can simply give it the letters we want to initialize the array with. But we don't write this out like this, because that's inconvenient. This is special syntax for arrays, which we needed because we declared our own array. This is already an array under the hood, hidden from you, so we don't need to have that syntax. We copy the idea from characters, just instead of a single tick to denote a single code unit, we use quotation marks, double ticks, to make sure we have more than one code unit. We have several code units. And we can write out the full text. Check something? Yeah, okay. I have to wrap it up slowly. Text now holds this full text. Internally, it is still just an array like this one. An array, just a standard array of characters of 16-bit values, where the values in order represent the code points, or code units technically, but they match up to the code points for H, E, L, L, and O. Combined, they would give you the text hello. The computer doesn't understand the text, just knows there's an array of characters in this order. The human would see this as the word hello. The computer doesn't care about that. It's just a series of numbers in the end. And because this can store a sequence of code units, this is where we can do this as well. I think the editor just got a bit weird. Let's try that again. Okay, that's better. This is fine. We specifically told it we want a sequence of code units. We want an array of characters. So this will have two code units, two 16-bit code units to form one UTF-16 formatted code point. So an array with two entries, and that's stored in text, which looks like just a normal data type. And we can do certain things with this that we can do with normal arrays as well. So with letters, I could go letters.length to get the number of entries. 1, 2, 3, 4, 5. And with text, I can do the same, because it is basically an array. I can go text.length and I get the number of entries. If this was hello, I would get 5. If I don't have anything in here, it's still a valid array, just with 0 elements, so I get 0. And with this, I would get 2, because internally I have 2 characters. Even though you only see one symbol, that's only what you see. Internally, it's 2 code units, which means you have 2 characters. And to access individual characters, I can go 0 or 1, 2, just like a normal array. And so I can go here and also go 1, 2, and 3, and that way get specific characters from this text, which is only too long, so this is invalid, but this way. If I do this, C will have the second code unit that is required to make this car. One thing that doesn't work though, because string is special, letters 2 is what I should use. Letters 2 I can just replace with a different character. this would change this to that. And that's valid. I can do that. This is not valid. Strings are special in that they are read-only. I can reassign text, that's no problem. I can say text is now something entirely different. This is valid. But I can't change the characters within text. If I access individual characters from this array, or from this array, I can read them, but I'm not allowed to write. I can read, but not write. Individual characters. I can still change text to some other text. But once we have defined a string, this sequence of code units, this one sequence stays intact throughout your entire program lifetime. You can create new texts. You can create new texts based on this one, and you can drop this value entirely. But this one sequence that's stored somewhere in one point in your memory will stay exactly the same forever. Which is important for a lot of systems. It's also important for efficiency. If the same text appears several times in your program, we do it here and maybe bring another, which will also get this car. The computer will make this more efficiently, and it will store this sequence of code units once somewhere in memory, and it will reuse that same sequence whenever you create a variable instead of reserving new space and storing that and everything. If you write out a full sequence like this with these quotation marks, the computer will make that more efficiently and store that in your program once. Which is another reason why it's important to not change it, because it's basically a static variable in that case. It's almost like a static field. There are a lot of other things you can do with text, a lot of fancy stuff. You can do, just an example, we can do text.substring, for example, which would give you another string. So if I do hello, for example, and go substring, then sub would be HE. So lowercase e. Or 1, 2, that would be EL. So you can extract text. Those operations you can perform on this type. It's a reference type. There's a full class with all kinds of fancy methods you can use. And there are a lot of other things you can do with strings. One of the most common ones maybe. Oops. You can concat text as well. You can extract parts of one string, and you can create a new string that combines the characters from one and another to one new text. So sub would now also be hello. Just an example. We will get to see a lot of strings and string operations over the next couple of episodes, just as a side note. The most important thing is that you understand we have string as a type. It's a reference type because it's essentially wrapping a character array, and it shares a lot of similarities with a character array. And characters themselves represent numbers, 16-bit numbers, so they are more like short actually, well, U-short. And these numbers are code units according to the UTF-16 encoding format, which is ultimately a system to combine one or two code units to form one code point, which in the end is a single integer number that references a specific row in an internationally managed table full of unique characters and symbols and drawings and character modification codes and whatnot, which we usually refer to with Unicode. And that's all I'm gonna say for text for today. It's not that much in terms of programming knowledge here to pick up, but I just wanted to share some background knowledge and I got a bit distracted by the history. Which is fictional, by the way, made that up. That's just one way you might think about how this came to be. You can read up the history of Unicode and formatting and whatnot in your own time. Alright, with that, I'm gonna leave you. Have a lovely Sunday and see you next time.